Hello, my name is Jacqueline Garrahan. I'm a senior machine learning engineer at Aiera. I've been working in the natural language space for several years. I started working at Aiera back in 2018. In 2020, I took a brief hiatus from Aiera in the language space to work on machine learning infrastructure for control systems in particle accelerators at the SLAC National Lab. In 2023, I rejoined Aiera just as the current generation of transformer models began to reach maturity. I'm excited by model evaluation, and today I'll share with you a brief case study that we conducted at Aiera into developing a high-quality summarization data set for earnings call transcripts. I'll begin with a brief intro to Aiera. We are an investor intelligence platform that focuses on empowering our customers to cover a large number of events and surface timely insights. We provide real-time event transcription, calendar data, and content aggregation, as well as enrichment. Our product is delivered either through our UI experience via our web or mobile apps, as well as through embeddable components and API feeds. Aiera covers over 45,000 events per year with a team of agents responsible for ensuring consistency of connection, the quality of audio in transcription, and data intake. Event coverage includes earnings presentations, conferences, and regulatory and macro events. Our other data includes a variety of content, including filings, event slide decks, press releases, client documents, and news feeds, among others. Aiera's AI efforts aim to enrich our data with a constellation of generative insights. We have 4 main categories of AI functionality. We use models for a number of utility functions such as text cleaning, restructuring, and the generation of titles. We also conduct transcription of recorded events, then extract topics, entities, and speakers from transcription text. Metrics provide additional intelligence, like topic relevance rankings, sentiment analysis, and tonal sentiment analysis of recorded speech. Finally, we have a series of more complicated insights like SWOT analysis, Q&A overviews, and event summarization. A couple of months back, we began the process of building a comprehensive data set from Aiera's earnings call transcriptions for use with large language models to power automated summarization. There are 2 main categories of summarization tasks, extractive and abstractive. Extractive summarization selects key sentences or phrases directly from the text without changing their wording. It's essentially about identifying the most important parts of the content and compiling. Because this approach doesn't quite generate new language, it's easier for large language models to perform extractive summarization. On the other hand, abstractive summarization involves generating a condensed version of the original text by creating new phrases or sentences. Instead of pulling directly from the source, it rewords and paraphrases the main ideas into shorter, more coherent summaries. This process requires a deeper understanding of the text, making it more challenging for large language models since they need to generate new language rather than just recognize what's important. In summary, while extractive summarization is simpler and faster for models, abstractive summarization offers a more natural and flexible output by paraphrasing the content rather than copying it directly. Our generative summaries are required to accommodate variable length transcripts, and therefore, we require models with large context windows. We also require financial domain intelligence. Our summaries need to reflect what is important to our clients, investment professionals. This can be accomplished through specific guided prompting. Finally, we require concise summary outputs so that our users can understand the crux of the call in an easily digestible format. There have been several open source efforts to create model benchmarks for financial tasks. One example is P-Shoe, which is available on GitHub and was compiled in a multi-university effort. The benchmark contains references to Hugging Face datasets for specific tasks. None of the publicly available datasets worked for us out of the box, so we decided to build our own off of Aiera's transcribed event data. To compile our dataset, we first assembled the transcript portion by pulling speaker names and transcript segments from a subset of Aiera's earnings call transcripts. We assembled these into a single text body to be used downstream in templated prompts. Then, using these transcripts, we automatically extracted a number of targeted insights to give the model an indication of what would be important for an investment professional. For this step, we used the February release of Anthropic's Claude 3 Opus, which was the highest-ranking model on Hugging Face's Open LLM leaderboard on text comprehension tasks at the time of analysis. We compiled a list of guided insights for use with the model, specifying a number of focus areas, including financials, operational highlights, guidance and projections, strategic initiatives, risks and challenges, and management commentary. In order to instruct the model to compose summaries consistent with our derived insights, our prompt needed to include the guidance for the model with respect to what it should surface. We distilled the insights down to their parent categories and provided some examples. The prompt was formatted into a templated task along with evaluation instructions using Eleuther AI's LM evaluation harness. The harness was then used to summarize the reference transcripts from our dataset and the generated summaries for scoring. Next, we tested a number of scoring metrics to evaluate model performance on the summarization task. Scoring generative text tasks like summarization is difficult for a number of reasons. First, quality is subjective. Summarization often involves subjective judgments about what makes a good summary, and these judgments are highly user and domain specific. Second, language is complex. Human language is full of context-sensitive expressions. Third, there's no single correct answer for a good summary. There can be many correct ways to summarize a piece of content, varying in structure, length, and detail. Finally, evaluation metrics themselves are a challenge. Standard evaluation metrics may not adequately capture the quality of alternative, yet equally valid summaries. Many projects use Rouge scores as a measure of generative accuracy. Rouge helps us understand the extent of overlap between the content of machine-generated summaries and our reference summaries. Let's break down the different types of Rouge measures. First, we have Rouge N. This metric measures the overlap of n-grams between two summaries. An n-gram is simply a sequence of n words used together. For example, Rouge 1 looks at the overlap of individual words, or unigrams, while Rouge 2 examines the overlap of pairs of words, or bigrams. Next, there's Rouge L, which focuses on the longest common subsequence between the generated summary and the reference. This helps us evaluate how much of the longest sequence of words that appear in the same order is captured by the machine-generated summary. Lastly, we have Rouge S, which we won't use in this analysis. This measures the skip bigram overlap, where two words are considered a match if they appear in both summaries, regardless of the words in between them. For our preliminary analysis, we've chosen to evaluate our dataset using Rouge N and Rouge L. First, let's take a look at Rouge N, which measures the overlap of n-grams between a candidate summary and a reference summary. Precision in Rouge N is calculated by dividing the number of overlapping n-grams between the candidate and reference by the total number of n-grams in the candidate summary. It shows how much of the candidate matches the reference. Recall is the ratio of overlapping n-grams to the total number of n-grams in the reference summary. This tells us how much of the reference is covered by the candidate. The harmonic mean of precision and recall is used to calculate F1. Rouge L focuses on the longest common subsequence between a reference and a candidate text. It's particularly useful because it considers the order of words, unlike some other Rouge variants. Precision is calculated by dividing the length of the longest common subsequence by the total number of words in the candidate summary. This tells us how much of the candidate's content matches the reference. Recall, on the other hand, is determined by dividing the length of the longest common subsequence by the total number of words in the reference summary. This measures how much of the reference summary is covered by the candidate. Once again, the F1 score is the harmonic mean of the precision and recall. In summary, precision evaluates how much of the candidate is correct, recall assesses how much of the reference is covered, and the F1 score balances the two. Now let's calculate various Rouge scores using an example. Our target will be the cat jumped onto the windowsill, and our prediction is the feline leaped onto the window ledge. We can see that despite our target and prediction having mostly equivalent meaning, all of our scores are below 0.5. Because Rouge scores range from 0 to 1, with 1 signifying a perfect match, we're given some indication that the Rouge metric doesn't accurately capture the near equivalence of the two sentences. The Rouge metric is attractive because it's simple to compute, measures content overlap directly, but it is better suited for tasks with a lot of exact matches between words or phrases, such as extractive summarization. Some other weaknesses include that it ignores semantics and context, it favors word-level similarity, so it doesn't handle paraphrasing well, and it often rewards longer summaries due to recall bias. BERT scoring is a modern alternative to Rouge that leverages deep learning models to evaluate summaries based on semantic similarity rather than simple n-gram overlap. Unlike Rouge, BERT scoring uses contextual embeddings to capture the meaning of words and phrases, allowing for a more nuanced comparison between the candidate and reference summaries. This makes BERT scoring particularly effective in cases where summaries may use different words but convey the same underlying meaning. Instead of comparing the raw n-grams or sequences, the BERT score creates embeddings for both the reference and generated summary in a vector space, breaking each sentence into tokens, which could be words or subwords. The cosine similarity of the tokens in the generated and reference summaries are calculated as a measure of the similarity. Cosine similarity measures how close two tokens are in meaning, with values ranging from -1 to 1, where 1 means they are identical. These similarity scores are aggregated over the entire text bodies. Because the BERT score is designed to capture semantic similarity, it performs well even when the generated summary uses different wording or paraphrases but retains the same meaning as the reference. Like Rouge scores, precision, recall, and the F1 scores are computed against the BERT score to gain insight into quality. These scores range from 0 to 1, with 1 signifying a perfect match. To calculate the precision, we find the highest cosine similarity score with any token in the reference text for each token in the generated text. The average of these maximum scores across all tokens in the generated text gives us our precision. For recall, we find the highest cosine similarity score with any token in the generated text for each token in the reference text. We then average these maximum scores across all tokens in the reference text to calculate recall. Finally, we combine precision and recall using the harmonic mean to get the F1 score, balancing both measures. Now, returning to our earlier CAT example, we compare our Rouge scores to the BERT scores. While not a perfect match, we can see that BERT does a much better job of suggesting the equivalence of the two statements. Our next step in exploration was applying BERT scoring to our summary dataset. Here, we report the BERT F1 scores across a number of models and providers. Recall that the F1 score provides a balanced metric of both precision and recall. We found that Anthropic's latest model, Claude 3.5 Sonnet, was the winner. When we plot a comparison of F1 scores across our Rouge and BERT measures, superficial inspection suggests that there is some correlation between the Rouge and BERT scores. So we calculated a correlation matrix from the results and found statistically significant correlations across measures, suggesting that even the lower values reported by the Rouge scores can serve as an adequate metric for comparison. BERT scoring offers some distinct advantages over traditional metrics like Rouge, but it also comes with a few trade-offs. Let's start with the strengths. First, BERT score captures the deeper semantic meaning, moving beyond surface-level word overlap. This allows it to recognize when two summaries convey the same idea, even though they are using different wording. Second, it handles paraphrasing well, which is crucial in many real-world applications where exact wording isn't always necessary. Lastly, it's better suited for abstractive summarization, where the generated summary might not contain the exact words or phrases found in the reference, but still captures the main concepts. However, there are some weaknesses to consider. Calculating the BERT score is more computationally expensive in comparison to simpler metrics like Rouge, and requires more processing power and time. It's also dependent on the pre-trained model and its training corpus, meaning its performance can vary depending on the data that it was trained on. Finally, the BERT score might not be as interpretable as something like Rouge. Explaining why a summary received a particular score can be challenging since it's based on complex contextual embeddings. So, while BERT scoring brings powerful advantages for understanding meaning, it does require more resources and may not always offer clear, interpretable results. Because our scoring relies on embedding quality, we should consider whether the default embedding model is sufficient for scoring purposes. The BERT-based uncased model currently ranks at 155 on Hugging Face's MTEB leaderboard. lower than others with the same dimensionality. We calculated the BERT scores based off of alternative models. We selected the highest ranked models on the MTEP leaderboard with 1,024, 768, and 384 dimensions, respectively. Running our small example for each model demonstrates that the no-instruct 384 dimension model suggests higher equivalence between the two sentences. On our summary dataset, the no-instruct small embedding model doesn't necessarily give us any new information. If anything, no-instruct BERT scores appear to assign unreasonably high scores to the unstructured prompts, suggesting that something might have been lost in the dimension reduction. In close, though we've earned some indication that Claude 3.5 Sonnet is best for our use case, many questions still remain. First, how do stylistic differences impact performance? Second, does prompt favoritism or specificity impact model scoring? By that, I mean, because we used Claude 3 Opus to generate our initial set of insights, does this structurally impact the way that we're scoring? So, would different providers perform better with slightly different prompts? Third, are we losing important nuances by choosing a lower dimensional embedding model and conducting BERT scoring? Finally, what are the cost and performance trade-offs? We've learned that the degrees of freedom available in evaluating models on generative tasks makes model selection challenging. Some final takeaways. At Aiera, we maintain a leaderboard of task-specific benchmarks that you can reference when building your systems. Internally, we use these benchmarks and others to inform model selection and deliver high-quality generative insights to our clients. The leaderboard, which is available on Hugging Face Spaces, hosts scoring for major model providers such as OpenAI, Anthropic, or Google, as well as large context open source models available through Hugging Face's serverless inference API. Thank you for joining me. Once again, my name is Jacqueline Garrahan. Please feel free to reach out to me on LinkedIn with any questions about Aiera or our AI Insight Engine.